Hello, I'm Mike, and my research is about deep learning-based power allocation in massive MIMO systems with different loss functions. The objective of my research is to develop and evaluate the performance of the novel loss function called sum rate-based mean square error with traditional loss functions, and to feed each of the networks with different loss function implemented with different number of datasets to extract the data scarcity of each mode. As we are moving into the era of mobile communications, data traffics are growing rapidly. Millimeter waves and massive multi-input, multi-output system has been considered to build a larger bandwidth system to handle such demand. The base station employs three-dimensional angular-based hybrid precoding, which will decrease the channel state information overhead and the required hardware complexity. The 3D APHP consists of three stages, namely the radio frequency precoder, the baseband precoder, and the multi-user power allocation block. Our goal is to optimize the power allocation in order to reduce the communication latencies between devices, which can improve the communication experiences with existing hardware, as well as avoiding unnecessary incidents that is caused by the latency. In previous work, particle swarm optimization has been implemented to find the global optima of the power allocation algebraic space. However, this approach has a very high time cost. Therefore, we propose of using a deep learning techniques called fully connected neural networks to simplify this process. To control the variation of the experiment in the study, each of the neural networks has the same structure, which consists of 300 layers. And the inputs consist of two variables, namely the affected channel and the baseband precoder. For each of the header layers, the activation chosen is ReLU. And at the output, we use another sigmoid function to ensure that we have a positive and between 0 to 1 output. In terms of the loss functions that we're investigating in this research, we chose 4 classic regression loss functions. And each of them are power-based, which means they are using the predicted power allocation and compare it with the label power allocation to generate loss. And in order to get our proposed sum rate-based mean square error, we need to first calculate the sum rate using the generated power allocation from the neural network and the label power allocation. And after that, we will take the MSE between the predicted sum rate and the label sum rate. After using 35,000 data to train each of the neural networks, we use another 1,500 independent datasets to test each of the networks in terms of the average sum rate. And our proposed sum rate-based mean square error approach neural networks yields the best overall average sum rate compared to all other neural networks. And in terms of the training loss, our proposed loss functions neural network has a very close overall sum rate output compared to the label sum rate, which indicates that with more training data in the neural network, it will generate an even higher sum rate output. After feeding different number of training data sets into each of the training network, we can see that our proposed sum rate-based neural network consistently generate the highest overall average sum rate among all other neural networks. And we do need at least 35,000 data sets to train the neural network in order to get an exceptionally good sum rate output. And the conclusion is that the fully connected neural network using the proposed sum rate-based MSE loss function generates the best prediction result among all other neural networks. It has successfully improved the performance of the massive MIMO system. It has a great potential in the field of communication. However, further hyperparameter tuning is still required to extract the full potential of this fully connected neural network. In the future, we will try to merge this loss function approach with other type of deep learning models, such as CNN and RNN, to further improve the network's prediction. Thank you all for listening to my presentation.